Hi everyone, I'm Paulito of IBM Research. I'm going to talk about distributed AutoML pipeline search in PC and RasPi K8s cluster. These are my collaborators. There are several reasons why I'm interested with this project. First, there's a growing need for low-power computing devices for HPC applications, such as in weather forecasting and many others. Raspberry Pis are cheap, versatile, and has great Linux hardware support, as well as stable Julia releases, which make this implementation trivial. The combination of Julia, RasPis, and K8s can provide a good platform to solve machine learning pipeline search optimization tasks, especially for IoT and edge computing with minimal energy footprint. This is the typical image of the Raspberry Pi 4, which is the latest iteration of Raspberry Pis. It costs around $35 or 35 euros. It supports 1.5 to 1.8 GHz clock speed, quad-core, 64-bit CPU. It requires less than 5 watts of electricity, and because of this, it can run off-grid easily by battery or solar power. These are the RasPi cluster options. The first two on the top are DIY cases, which cost only around 35 euros, while the three at the bottom are the specialized hardwares that support much faster networking, routing, and expansion boards. This is my DIY Raspberry cluster at home. Currently, I have only 2 RasPis because of the supply issue. The price after market is more than 3 times from the regular price. These are the lightweight implementation of the Kubernetes clusters, targeted for machines with minimal resources, such as the RasPis. In our case, we're using the K8s by the Rancher Labs to implement and to deploy our applications. And here's the outline of the demo. First, we will start with a simple use case of running the AutoMLPipeline parallel search in the local machine. And then we're going to deploy our application. But before that, we will show to you how to create the K8s cluster in a bunch of PCs using the Ansible automation script, and then how to do automatic creation of K8s cluster in Raspberry Pis using the K8s Ansible automation. And finally, we're going to show the example deployment of AutoMLPipeline application in K8s cluster for both PCs and RasPis. Note that the demo contents can be found in our GitHub repo in the examples directory. In summary, Julia and RasPi and K8s work very well in practice, and the succeeding demos will try to convince you. Let's have a short demonstration of what the application looks like if run in a local machine. So let's load the necessary packages, set the seed, spawn several workers, load the main algorithm, the 2-blocks pipeline algorithm, and then we're gonna load the data set, and then let's run the actual 2-blocks pipeline search, which will do the parallel searching across 8 workers in the local machine. This will run a bit, so let's forward the video so that we can see the final result. So here's the final result. You will see that they are arranged from the best to the worst, and even the worst is still better, like at 92% accuracy, but the best can reach 98%, and it is in this pipeline. RBFSVC seems to be the best model. Before deploying to the Kubernetes cluster, let's now highlight the changes that you have to make in order for your application to be Kubernetes ready. So in the left pane, you will see here the application running in the local machine, and in the right pane is the example application that is supposed to run in the Kubernetes cluster. What you'll notice here is that the major difference will be on the call of the add procs command, because in the local machine, you only need to have the distributed package responsible for distributing the workers, but in the Kubernetes cluster deployment, you need a K8s cluster manager that is responsible for distributing the workers across the different Kubernetes nodes. And then you also have to add the way for you to be able to pass arguments that would indicate how many workers are available in that particular cluster. And then the rest are exactly the same. And then for the next thing that you have to do is to create the deployment files. First, you need to create Docker images, and depending on the target architecture, whether it is Intel or ARM processors, you have to build a specific Docker image specific to that target architecture. So on the left pane here, you will see deployment for the Intel processors, and the right pane is for the ARM processors or for the RasPi Kubernetes cluster. The major difference is that base Julia image is running Intel, So if you're interested to run it in a ARM processor, you have to use the Julia-based image that are based on ARM processor. So this is the major difference. The rest are the same. And then you have to build the package. So here, this is for the Intel target. So the name is Docker build -t in AutoMLPipeline Intel. The right side, it is for the ARM processor. And then once you build it, you tag it for the registry. So this is the name in my registry, and then tag that this is for the Intel and this is for the ARM. And then you log into your Docker registry hub, and then you push the Intel image and the ARM processor image, and then pull this image depending on which cluster you're gonna use. So lastly, you have to create a deployment to deploy your program. And here the difference is that if you're running Intel cluster, you're gonna use the AutoMLPipeline Intel. That is the Docker image that is built for Intel. Otherwise, if you're going to use it in a RasPi, you have to use the Docker image that is built for the ARM processor, and the rest are the same. Let's now proceed with creating our cluster. So to create a cluster in Ansible script, you edit the inventory file or the host file, wherein you list down your machines. On the left side is the inventory file for the Intel processor. So I have one master with no GPU, and then several workers with GPU and several workers with no GPU. On the right side is the list of my machine for the Raspberry Pi cluster. So there's one machine which will become the master, and then another machine which become the node. You can increase the number of Raspberry Pi workers here, but because of the supply problem, I can only have 2 RasPis at the moment. Let's now run the Ansible script to create the Kubernetes cluster targeted for the Intel platform. So as you may recall, we have several workers and one master, and some of these workers have GPUs. Let's skip the video so that we can see the final result after. Now we are done with the script, and as you've noticed, the Ansible script created one master node, which is called the control plane or the master, and then 1, 2, 3, 4, 5 worker nodes. Now that we have the cluster up and running, we can now deploy our application. So our application starts with the main orchestrator, and then the main orchestrator will spawn several workers across the different nodes, and this is the log of what's happening from the main orchestrator. So it's checking the other workers if they are up, and then once they are ready, this main orchestrator will assign tasks to each of these workers. So this shows here the number of workers and the master node of our Kubernetes cluster. So after some time, when the workers are ready, the main orchestrator will submit jobs for them, or in this particular application, each one will receive a certain kind of a pipeline task to cross-validate. And once they are finished, the main orchestrator will collect all these pipeline results and sort them according to their performances so that we can get the best optimal pipeline. Let's skip the video so that we can see the final result. Here's to show quickly the Ansible script to create the RasPi clusters. Let's skip to the last part. So now finally we have one master node for the Raspberry Pi and one worker node for the Raspberry Pi. Let's now deploy our applications of the Kubernetes cluster running in RasPi and use the K9 viewer and see what's going on with our main orchestrator running in the cluster. What you will see here now is that our main orchestrator is now running or assigning jobs to the worker. We don't have much time, so let me skip to the last part of this presentation. So we have 576 pipeline. So here's the final result. And this is the end of my presentation, and I'm now ready for your questions.